I won't hurt my feelings. It will hurt my feelings, but I will act like a professional. What a loser. All right, so so the only thing we have left now is the final. So oh, okay. I thought it took you that long. Okay, shut up. Okay, the only thing we have left now is the final, and you have 2 chances to take that. Monday, 12/11 at 6 p.m. in 1326. And then the other one is Thursday, 12/14 at 2 p.m. in this room, 1328. And remember that this is cumulative. I mean, all these tests are, but so, you know, if you're, you know, it can be sort of overwhelming to think about like how to study for the whole semester worth of stuff. What I would recommend doing, if you don't, like I assume most people won't have time to work through every problem again, but if you did have time to do that, that would be the best thing you could do. But I would recommend just start with that first set of problems and go through and just, with each problem, ask yourself, do I know the steps to do this problem? You know? And if you do, then you're probably good with that and you can go on to the next one. And then when you get to ones where you're not really sure what to do, those are the ones to spend some time on. You know, hopefully that'll significantly cut down on the number of problems that you have to actually write out and do. Yes? Probably not. It's just all, I mean, you know, I just have a big pile of stuff and I'm just trying to grade it as quick as I can. I would say just try to get ready without them. That's all I can. What? Those are graded, yeah. Those you can have back. I haven't given those to you yet? Oh. Yeah, I have them. Should I run up and get them? Okay. Anyone remember what we were talking about last time? Yeah, so from last time, we're starting to talk about conservation of energy. I'll write it as the work energy principle. And the work energy principle in certain cases is going to turn into conservation of mechanical energy. And so the work energy principle, remember, says if you add up the total work so calculate the work that's done by each individual force, add those all up, that's equal to the change in kinetic energy. And you can calculate the work as a dot product between the force and the displacement vector. And if the work is positive, it means that it's that the things, your chosen object, its kinetic energy is increasing. And if the total work is negative, it means the kinetic energy is decreasing. There's one difficulty with this. And when I gave you the formula for work, I didn't really talk about this, but that formula that I gave you for calculating work is a simplified formula. So the problem is work isn't always easy to calculate. Because if you think about it, remember that the work is equal to the dot product of the force with the displacement vector. But if something's moving through a finite displacement, it takes some amount of time to do that. There's nothing to guarantee that that force is going to be the same the whole time. So this formula that says work is equal to the force dotted with the displacement, it only works if the force is constant, if it stays the same over the whole displacement. So that's a big drawback. For certain types of forces, though, we can get around this. So we can always get around this. This problem, this difficulty. For a type of forces, so you can't, with some forces, there's nothing you can do. But for a type of forces that are called conservative forces, there's an easier way to calculate it. So I need to first talk about conservative versus non-conservative forces. Okay, so what's easier to deal with, conservative or non-conservative forces? Conservative, yeah. The calculation is easy if you have conservative forces. Non-conservative forces in general are more of a pain to deal with. So a force is conservative if knowing the object's position is enough to know the force vector. So let me give you a couple examples of things that are and are not conservative forces. So let's talk about, let's think about the forces that this table applies to this table. There are two kinds of forces that can apply, a friction force and a normal force. So first, let's talk about the normal force. So say I know this is we're dealing with this table with this stapler. We know the masses of those things and stuff like that. Is it enough if I can specify that the stapler is in this exact position? Is that enough to know what the normal force is? At first, you might think it is because when it's just sitting here like that, the normal force is counteracting the weight force. So that's a reasonable thought. But think about this. So right now, if, well, let's say this has a mass of 0.1 kilograms, 0.1 kilograms. So then the weight force is 0.981 newtons, right? So right now the normal force is 0.981 newtons. But now if I push down on it like this, it's still in the same location, you know? But now the normal force has to counteract both the weight and the force I'm putting down into it. And so right now, the normal force is quite a bit bigger than 0.981 newtons, even though the location didn't change. Okay, so that normal force is not conservative. Anybody have any questions about that? Like, yes, you do? No normal forces are conservative, yeah, because it's not, so think of the normal force is like if this was on a bathroom scale, okay? What does the bathroom scale read? Is it enough information to know what the scale would read if to specify the location? And it's not, because right now it reads 0.981 newtons, now it reads 10 newtons or something, okay? And it's in the exact same location, so that's not enough information to specify the force. What about the friction force? Is the location enough to specify the friction force? That's definitely not, because it could be in that location moving this way, and then we know the friction force points opposite the velocity vector. Or it could be in that location coming this way, and then the friction force is the other direction. So those are all cases where the location is the same, but the force is different. So those can't be conservative. Okay. All right, well, what's an example of a conservative force? There's only two types of conservative forces that we're going to deal with. So you're like, well, why didn't you just leave out the rest and just tell us the two and we'll memorize those two? And that makes sense. Well, one of them is gravity. And in fact, gravity is even more predictable than a conservative force has to be. Because, so say this has a mass of 0.1 kilograms. What's the force that gravity applies to it when it's in this location? 0.981 newtons down. What is it in this location? 0.981 newtons down. So the location doesn't even matter. You don't even have to tell me the location, and I know the force that's applied to it. Okay, so if you give me the location of this stapler, I'm going to ignore what you said, and I still know the force. You know what I mean? So the weight is a conservative force. And then the other one is the force that a spring applies to things. So the way that works is if you have a spring and you know how stiff or flimsy it is, you know how hard it is to pull it out half a meter, whatever distance. And you attach this stapler to the spring, and then you tell me how far you pulled it out. That's enough information to know what force the spring is applying to it. If you pull it farther back, the spring is going to apply a bigger force. If you push it, like, so say this is where it would be if you didn't stretch it or compress it. If you push it in, the spring is going to push back that way. And all of that is totally determined by the location of the thing attached to the spring. So here's some non-conservative examples. The normal force, friction forces, cable forces. Again, with a cable, you know, like you could, if you think of something swinging around a cable like in a circular motion, and you say, okay, right here is where I want to know the force that that cable is applying to the object. Is that enough to know the force? No, because we know if you swing it faster, that cable tension is going to go up. Or if something else pulls against the cable, that force is going to go up. So these are examples of non-conservative forces. These are a pain. That means with bread in French. Then the conservative forces, there are only two examples we're going to deal with. And these are the ones we like. These are the easy ones. The first one is the force applied by gravity, the weight. And the second one is the force applied by a spring. And what makes conservative forces easy to deal with is that for conservative forces, you can define a thing called potential energy. So conservative forces have a thing called potential energy. Non-conservative forces, there's no such thing as potential energy. And the work done by conservative forces can be calculated as the work is equal to the negative change in the potential energy. So if you calculate the potential energy at one location, the potential energy at the other location, subtract those two, that's a way to calculate the work. And you don't have to worry about all the complexities of calculating the work that you do for non-conservative forces. So here's the potential energy function for, the potential energy for gravity, for the weight. I'll call it PE gravitational, and it's equal to the mass of the chosen object times g, that's 9.81 meters per second squared, times the height of the object. Where h is the height above whatever you're calling zero height. So before you start a problem, you can say, okay, in this problem, I'm going to say the zero height is the floor or the top of the table or the center of the earth in some cases, But you just have to be consistent about what you're calling your zero height through the whole problem. And the potential energy for spring forces, I'll call that PE spring. And that's equal to 1/2 times this constant k, I'll talk about what that is, times x squared, where k is the spring stiffness, and x is the distance from the spring's resting length. K, by the way, has units of newtons per meter. If you have a big value of k, it means the spring is really hard to deform, and a small value of k means that it's really flimsy, really easy to stretch and compress. So that's potential energy, and the reason that we're using it is when there is potential energy, if we're dealing with conservative forces, it makes it really easy to calculate the work that the forces do. And you know, the work shows up in the work energy principle, so that's good. But there's still, you know, so that makes it easy to calculate the work done by gravity or spring forces. But almost always there are other forces in a problem besides gravity and spring forces. So it's like we would still probably have to calculate the work in those kind of problems. But actually, in a lot of problems, even though there are non-conservative forces, those non-conservative forces don't do any work. So let me show why that is. So often there are also non-conservative forces. And even though the force isn't zero, they don't do any work. And the reason for that is, or the way it works, is if a force is always perpendicular to the object's velocity vector, that force does zero work. So what are some examples of that? Well, it turns out that there are two super important cases where that always happens. The first one is normal forces. So a normal force, when something's sliding or rolling, you know, imagine a box that's sliding down an incline. the velocity vector is parallel to the incline. The normal force is perpendicular to the incline. And so those two are always perpendicular. And so even though that's a non-conservative force, you don't have to worry about it in the work energy principle. The other example that comes up all the time is a cable force let's see. So the cable force and an object is swinging in a circular motion. In this example above, okay, so the velocity is like that, the normal force is like that. You can see they're perpendicular. So let's think about the case where an object swinging in a circle. If it's swinging this way, the velocity vector is like that, tangent to the circle. The force applied to it by the cable is that way. And those are always perpendicular the whole time around. So what this means good news is when these forces act on the chosen object, they don't appear in the work energy principle. You can just skip them because they don't do any work. Okay, so what we saw is that for conservative forces, you can represent the work done by conservative forces as the negative change in potential energy, and the work done by normal forces and cable forces that are, centripetal pointing cable forces, those don't do any work at all. So if the only non-conservative forces are normal forces and centripetal cable forces, we'll start with the work energy principle. It says that the total work is equal to the change in kinetic energy. But since there aren't any non-conservative forces, we can just write this total work as the negative change in potential energy. So the negative change in potential energy is equal to the change in kinetic energy. And you can rewrite that as the potential energy at some later instant minus the potential energy at some earlier instant. Whoops, these should be negative. No, erase that line, sorry. Let me first write it like this. So 0 is equal to the change in kinetic energy plus the change in potential energy. And you can write that as the kinetic energy at some later instant minus the kinetic energy at some earlier instant plus the potential energy at some later instant minus the potential energy at some earlier instant. And rearrange it one more time, and you get that if you add up the kinetic energy at instant 1 and the potential energy at instant 1, that's equal to the sum of the kinetic energy at instant 2 plus the potential energy at instant 2. This is the conservation of mechanical energy. And the idea is that at any instant, the kinetic energy plus the potential energy is the mechanical energy. Can you always use this equation? No. What are the restrictions on when you can use this conservation of mechanical energy? So you can use this if the only non-conservative forces, well, if there's none, then you can use it, or if the non-conservative forces are normal forces and or cable forces with the thing swinging around in a circle. Okay, in those, and that's going to be most or possibly all, I can't remember, of the problems I give you, but then you can use this equation. But if you have friction or any other non-conservative forces that aren't normal forces or cable forces, centripetal cable forces, then you have to use the full work energy principle. Okay. So let me show you how this works, because it's pretty awesome. Okay, so let's say you're on your bicycle. Thanks. Well, this is your bike, I said. And let's say that you're at the top of this hill that's like, how high should this hill be? Like 20 meters high. Okay, that's just the height. And notice, like, the surface changes the whole way. I'm not going to specify anything about the shape of the hill. It doesn't even matter. Okay, it doesn't come into this calculation. And let's say, okay, so this kid starts fast at the top of the hill. If you ignore air resistance, how fast is he going at the bottom of the hill? And just to make the calculations simple, let's say it turns out it wouldn't even matter what his mass is, but let's say we know his mass. Let's say it's 20 kilograms. Oh, he has a bike too, so let's say 30 kilograms. Well, let's think about what forces are acting. First, there's gravity. What other force? Normal force on the bottom of the wheels. And that's it. We're ignoring all air resistance and friction. We're also assuming that his wheels don't, but basically we're assuming his wheels are super light. Okay, so the weight is a conservative force. So calculating the work done by the weight is easy. The normal force is non-conservative, but it's one of those good ones that doesn't do any work. So we can use conservation of mechanical energy. And that says that if you calculate the kinetic energy at one instant plus the potential energy at that first instant, that's equal to the kinetic energy at the second plus the potential energy at the second. Okay, so let's set up sort of a table thing for the two instants. Instant one is what I'm going to call the kid at the top of the hill. And instant two is what I'm going to call the bottom of the hill. So let's first calculate the potential energy at instant one. We have the formula right up here for the gravitational potential energy somewhere. Right here. So we just take the kid's mass, multiply it by 9.81 meters per second squared, and then multiply it by the height. In order to specify the height, we have to choose something that we're going to call zero height. What do you want to call zero height? might as well, yeah, the bottom makes sense. You could call the top 0 height, and then it would go to a negative height as it went, and it works perfectly fine. All this h equals 0. Okay, so at the top of the hill, the gravitational potential energy is equal to the mass times 9.81. Yep, because the negative is just a direction. And then times the height, which, what did I say, 20 meters? And so I think you get 5,886. What are the units? I didn't talk about that. But potential energy is a type of energy, so joules, yep. And now at the top of the hill, we have to calculate the kinetic energy. So if you remember that from last time, the kinetic energy is just 1/2 times the mass, 30, times the speed squared. What's the kid's speed at the top of the hill? 0, yep. So 0 squared. And so the kinetic energy is 0. And now we'll deal with the second instant that's at the bottom of the hill. The potential energy at instant 2 is equal to the mass times 9.81 times the height at the bottom of the hill. What's that? 0, yep. So that goes away. And then the kinetic energy at instant 2 is 1/2 times 30. And what's his speed at the bottom? That's what we're trying to find. So I'm just going to write that speed as v, square it to match the formula for kinetic energy. And conservation of mechanical energy says this plus this, these two things at instant 1 are equal to this plus this. And then we can use that equation to solve for v. So conservation of mechanical energy says 5,886 plus 0 is equal to 0 plus 15v squared. And so divide both sides by 15, take the square root of both sides. Speed is always positive. Can someone calculate what v is? 19.81 meters per second. That's probably not very realistic because if you're going that fast, there's a lot of air resistance. But if this was happening in a vacuum, this would be very close to what you'd really see. There'd be a little friction due to the wheels. There'd be a little effect of the wheels having weight that we won't get into. But yeah, very fast. So be careful if you do that. But that's cool. I mean, I think it is, because we don't have, like, if we were going to try to do this using Newton's second law, you could do it. I mean, it could be done. But you would have to know the shape of this hill at every instant. You'd have to have a representation for the shape of that hill as like a mathematical function. And then besides that, you would have to do an integration, which is a Calc 2 thing, of this function of normal. Like, it would be a very complicated thing to do. And what you would get after all of those calculations is exactly the thing that we just got in a one single equation, one line equation. And so for certain calculations, conservation of energy is a really much easier way to go. So notice, this brings up something that, this is kind of a first in this class that we've had. Now there are problems that we could actually sort of go in two different directions with. There are things that you could solve using conservation of energy that you could actually solve with Newton's second law. So now for the first time, we have to think kind of about what are indicators that we should go one direction over another direction. Okay. And so here is sort of the giveaway for whether you're going to use, if it's a good idea to use conservation of mechanical energy. So use this idea of conservation of mechanical energy. When you're looking for a relationship between an object's position and its speed. Okay. So you can also, like, as sort of a secondary thing, if the only non-conservative forces are normal and cable forces, that's another, whatever giveaway indicator. So yes, those cable forces, the thing has to be moving, swinging around the cable. Its motion has to be swinging around the cable, So centripetal cable forces. But if something's attached to a cable, I guess this would be the case anytime the other end of the cable isn't moving. So that's sort of what's required. The other end of the cable isn't moving. Then the thing would be moving in part of a circle around the other end. Yeah, pendulum is a good example of this. Yep. Any other questions right now? Yeah. Yes, that's right. In 2D kinematics, I give you more information. That's right. Yes, you're exactly right. So it does look like a 2D kinematics problem. I didn't give you enough information to just use 2D kinematics. Yep. Okay, let's stop there.